Does anyone need me to introduce COVID? I mean, if I do need to introduce COVID, I suggest you leave, wash your hands thoroughly, shower, and hide for the next I don't know how long. Otherwise, welcome to March. I probably do need some introduction. I like to do my intro is, hi, I'm Dom Davis. You may have heard of me. I know I have. I am a Go developer by day, and I do a lot of stuff with Neo4j and graphs, because I think graphs are wonderful. Why are you not? There we are. We should also introduce graphs. This is not a graph. This is a chart. Technically, this could be a graph, but actually is a chart. It could be the graph of the function x equals y, but I had to make it using a chart. And I'm looking at Fran here because she actually has the piece of paper that says that she can do math. I do not have the piece of paper. This is a graph, discrete math style graph. However, I'm not going to jump down your throats if you use the wrong definition of graph, because we live in a world where literally means figuratively now, and graph chart is not a hill I am willing to die on. So this is how Wikipedia defines graphs in a one restricted but very common sense of the term. A graph is, oh gee, no, I mean, I get graphs, I do graphs all the time, I read that, I can kind of understand what some of those symbols mean and they're getting at, but no. Pictures much better, much easier. This is a graph, it's a set of circles and lines, effectively. And we're going to call the circles, we can either call them vertices, nodes, or points. And the lines we can call edges, links, or lines. Or as I will later, relationships, because I like to be different. Now, you can have a directed graph. So a directed graph is got arrows on it and says that the link traverses in this direction, and you can add information onto those nodes. So you can sort of say that you've got node A traverses to node B, that traverses to node C. So we should probably write some code because that's why we're all here. And next excuse needs to come up. So. With these things, quite often people are not familiar with Go. I'm going to do all of this in Go. And people ask questions, and this conference, especially where we have a bunch of very bright C++ developers, they ask me questions I can't answer. And they ask me questions about newer features of the language, which may have come out. So yesterday I decided just to check what was new in Go. And they've released generics. And being a sensible speaker, I installed the latest version of Go so that I could play with generics. Because, hey, I can do a talk on a brand new massive language feature a day after I found out about it. No, I can't. However, I did manage to break my entire setup. So my linter isn't working, my main linter, but that's not an issue. The rest of it is. So we can go. So what we're going to do, we're going to try and make graphy stuff. And it's quite easy to do in a language with pointers. I mean, we can have a type of, so with Go, you prefix your types with type. I'm going to have a type of graph, and it's going to be a struct. Probably don't need to explain structs to C++ people. They're very similar. Go is very C-like. And we're going to have in there, well, there's going to be a set of nodes. And I think we probably need to define what a node is. So we're going to have a type node, and we're just going to have that as a string. No, string. Typing ability is inversely proportional to the number of people watching. There can be infinite people on YouTube, therefore my typing is not going to work. So we have a set of nodes, which is going to be a slice. Go has arrays. Arrays are fixed, and you cannot change their size. You generally don't deal with arrays. Instead, you deal with this data type of a slice, which allows you to have varying sizes and do all the appends and the goodness that you might get in, say, an array list or a vector type or something in another language. I'm showing my Java credentials there. So this is going to be a set of pointers to node. Pointers are quite a complex subject. If you are a C++ or C developer, and Go, they are simple. You have pointers, and that's about it. There is no pointer arithmetic or anything like that. The thing points to that, and you can dereference them, and there you go. So we're going to use pointers for reasons that will become obvious, and we probably want something that is a link. So we're going to have a type of link, and that's going to be struct type. And a link goes from a thing to a thing, so we're going to from a pointer, and this is why we're going to be using pointers, because we want to be going to the same, we want to go from to the same things. We don't want to be duplicating these things in memory, because sometimes graphs can get quite big. So there we are, we're going to have nodes, and we're going to have links, which is going to be a slice of the link type. So we've got a sort of a graphy data structure set up there, and we can do stuff with it. So we can sort of define our this one, where are we? Do I have one that I'm going to define? So let's put directionality in straight away. Let's define this one. We've already got directionality. We've got to and from. We want an A, a B, and a C. So we can turn around. Now Go has this sort of syntactic shorthand thing for assigning a variable in functions. So we can say that this is. And what I would normally do, because I normally use structs, is I would turn around and say that this is a pointer to a node, and because it's a string, we can do that, and we can do a node A. But the compiler's going to whinge at me. The compiler in Go whinges at me a lot. Go is a wonderfully opinionated language. There are this whole argument that I see coming here almost every year with where const should go. Const goes where the compiler tells you it goes, and that's where it goes. But my compiler is whinging because it can't dereference node, and so there's a couple of ways I can get around this. I could turn around and say that n is equal to my node, and then A is a pointer to that. So that would work, but I don't want to have to do that multiple times, so I'm just going to create a constructor-like function. Go doesn't have constructors per se. Structs are initialized with well-defined zero values. Everything has a very well-defined zero value, even if it's well-defined as nil, which is the null type. But we can make a function, and idiomatically it's new and then the thing you're making. So we're going to say new node, and we're going to take a name, we'll call it ID, and we're going to call it a string. Go puts its parameters and types the wrong way round in function calls. I'm not even going to defend it. I still get it the wrong way around some n years after I started doing this. And it doesn't help that I bounce between, we'll call it a language, JavaScript and Go. So yes, they are the wrong way around. Tough. Basically, the reason for everything in Go is it is because it is. And for this, we're going to be returning a pointer to a node, and then we can do our shenanigans in here. So we can do new node ID, and we can return a pointer to n. I'm assuming everyone is happy with pointers. Do shout if there's. I'm probably talking to the converted and all of you laughing at me going, there's basic pointers. My spacing in my code, I will point out now, I have my linter turned up to about 1 billion, and it is incredibly opinionated about spacing and what lines should be cuddled with what other lines, and I have got used to appeasing my linter, so if you see me randomly sort of moving lines around and putting spaces in, that's why. So now we can turn around and we can say that A is a new node, A. And we can do that another couple of times. Yoink. Lecturers at university hate me because I cut and paste all the time. You should never cut and paste code, apparently. Oh, yes, you should. Right, and now we need to set up our graph type. So graphy. Idiomatically, Go likes short identifiers. Now, I'm a little bit on the fence about this. I will use short identifiers if they are very close to where they're defined, and it kind of becomes obvious as to what that short identifier is. I tend to go for a little bit longer for some things, so I might use res for result rather than R. And also, sometimes you run out of letters in the alphabet. we'll see later a way of hooking functions onto types, onto structs, and they always idiomatically are a single letter, and quite often that can then steal the letter that you want. I'm getting looks of why would you do that? With Go, you don't question, you just do. Opinionated. If you want to express your inner artist, different language. I do a Go training course, and yes, that is like day one. It's very opinionated, but it's great because it means that all code looks reasonably the same, and it's easy to grok the whole language, most of it. And it's simple. And as I have become old, I like simple. You know, Scala is very clever, and I've had code where there's been a bug on a single line of Scala, and we know it's on that line, but we have no idea what that line is doing and how to fix it. You know, I can have 10 lines of code which aren't as clever, but I can understand them. Anyway, we're going to create ourselves a graph. We're going to take, and because this is a struct, we can just straight away take a reference to it. And our nodes are going to be a slice of pointer to node, and they're going to be A, B, and C. And our links are going to be a slice of pointer to link, and they are going to be, and because it knows, the compiler knows that what's in here is a pointer to link, it doesn't need me to specify things. And in fact, if I were to specify the type outside the curly brackets, it would highlight that and say, not needed. So this can be from A to B, and then we've got from A to C, and from B to C. And there I have a graph. Oops, output into the terminal is very C-like, so we've got the printfs and everything. And in fact, I learned something about printf in this morning's keynote, and I'm going to change a whole load of my code where I realize I've been doing stuff in a very dumb way. And yes, I'm looking forward to doing that. But anyway, let's print out our graph and see what we have. Let's see how useful this particular code is. So I will run that, and woohoo, we have a whole load of pointers. Now, I'm not about to let you look at the internal contents of my max memory because, you know, there's various things in there, and it may take a while. So let's make this a little bit more friendly. Go has this idea of duck typing, very much like Python. I love teaching C# and Java developers because they really don't get it. And I know they don't get it because I used to be a Java developer and I really didn't get it. But the idea is that you don't implement interfaces, you match them. So there is a predefined interface in the standard library called stringer. Go idiomatically, if you have an interface that has a single function on it, the interface name is function name . I use that most of the time, but there are linguistic levels where I draw the line and will not stick on the end of a word, and I will pick something else. There are, you know, there's standards and then there's crimes against the English language. So we can use stringer because I know that println will go off and see if the types you've passed in implement stringer, it will call their string function, and we can use this to our advantage. So we can turn around and say, right, let's hook a function onto node, and we're going to call it string, string, and it's going to return a string. Now this means that anything that is of type node now has a string function and is a stringer. So format.println will, all the format package will do stuff with it. So I can now turn around and I can say return format. Actually, I don't even need to know. I can just now I will do format.sprintf %s, and then we're going to have to do some shenanigans here, because if I turn around and say that, it's going to whinge at me here. It causes a recursive call because, of course, I'm putting my thing that is a stringer into a format, and you know, off it goes. Again, laughing quietly to myself in this morning's keynote because I get warnings when I do stupid things with sprintf. But what I can do is I can turn around and go, actually, this is a string. Please turn this back into a string. So now it'll handle the normal string semantics and get rid of that recursion. We can also turn around and we can say this is a stringer as well. And we can say this is going to be a return from printf. And what do we want here? We want %s. And there we're going to have l.from and l.to. And then the last piece of magic is ggraph. And you can kind of spot the pattern with how you name these things. And that's also going to be a stringer. And that's going to, that's going to have a loop. So we're going to, what are we going to do? We're going to have for, this is always one that catches people out. So in Go, while is spelled F-O-R. And while you are ranging over something, it's a variadic return. So I can accept a single variable back. So I can turn around and I can say range g.links, and what that will do is it will give me the index of the thing that it's ranging over. So that will give me 0, 1, 2, and that's not usually that useful. What I actually want is the link, but Go also whinges at you if you don't use a variable. I've got red underlines there. And I'm not going to use I, so we have this underscore operator, which says, I know there's a result coming, and I don't care. So you're explicitly stating your lack of needing that, which does help with a lot of sort of bugs, except for this particular thing with ranging over slices, because it is so easy to turn around and go for L : equals, and then wonder why you're not getting the autocomplete working, and you're thinking maybe my IDE's been done, so you try and compile it, and then the compiler blows up, and then you go, of course, I can't do that on an int. I need underscore, comma, and years down the line, I'm still doing that. Anyway, we can now, what we want to do is we want to we're going to make a slice of type string. We're going to do that len g.links. So this is going to go away and pre-create me a correctly sized slice. Everything in Go is really simple and really straightforward, and there's only one way to do it, apart from creating things, in which case there are too many ways. I think there's like 20 or 24 different ways of doing it, because that's what's kind of dropped out with the combinatorial thing, and you need about 4 of them. So I will generally do the : equals. Sometimes I'll use var thing type if I just want the default value, and make, if I know how big a map or a slice is going to be, or I need a channel. So we're going to make something the right size. So in fact, yes, I will use I in this, because now we can turn around and we can say that si is equal to, and I don't need the : equals here because it already exists, so I don't need to initialize it, and it's going to be l.string. And then we can do return, and this is one of my favorite functions in the strings package, join my slice of strings with that. And it does that highly annoying thing, or solves the highly annoying problem of trying to join together things with commas where you don't want the comma on the end. It does all that, hides it for you. So now I've got this. So now if I run this code, bum, 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 we have our graph, albeit in sort of tuples. Great. So we can make graphs in code. And I am pretty sure that you can change this to language that you use. Even if you don't have pointers, you'll be able to do things with maps and look up on keys and stuff like that. Brutally easy in C and C++. Great stuff. So we've done that. The next sort of step is what if you encode some information on the link? And this is why I like to call them relationships. How do these two nodes relate to each other? And you start ending up with a semantic sort of sentence. And I do talks based on this in terms of you end up with a basic sentence structure with subject, object, subject, relationship, object. And these structures actually work in most languages, although sometimes you have to move where that triple is because some languages are different, very different in some cases to English, but they all operate on those three basic premises, and they just appear in a certain order. So you can start using phrases like A transitions to B. So if you've got a state machine, state A transitions to state B, and you're now reasoning about your graph and reasoning about your data rather than just A is linked to B somehow. And this becomes very important later when we start having different types of link. So let's add the relationships to our code. Right, so a relationship. Well, we've got a link. I'm going to call that a relationship now. Refactor, rename, relationship. Yes, do the refactor. Just looking if the JetBrains representative is in here. No, they're not. It's a shame. My license is about to run out and I haven't had a freebie this year. It's one of the few programs I don't mind paying for. Right, so that has gone off and done that. Let's just quickly refactor that. So it's relationship R. So we've now got a more semantic name. One of the, I do believe that the second hardest problem in computer science is naming things. The first hardest will be my lightning talk later tonight. And you will see on my live streams that I bounce around and change names regularly as I get a better idea of the domain model in my head. I'm not wedded to names at all. And if I need to change the name of something to make it more semantically correct, I will. So we've got, actually what I'm going to do is I'm going to revert that. I'm going to go back to links because, looking at that, that needs to be part of, so the relationship is in fact, in the link. So this goes back to my sort of, I will bounce around with various names. And one of the things with Go is when you are, when you're documenting things, anything that starts with a capital letter is public. Anything that starts with a lowercase letter is private, or package scope, effectively. And if you are documenting, the Go standard says that you start with the name of the function or the type that you are documenting. And you very quickly realize that if you are going through the semantic sort of gymnastics in order to get your sentence to sound correct, you've probably got the wrong name. And I will quite often start writing the comment at the top and then get to a word and go, that's a better word, let's shift that, rename it, and off you go. So you would end up with like link to nodes, relationship. And now my warning's gone away, and that's all good. Right, so we've got relationships in there. We probably want to change our string output. So we're going to do that. Again, getting a warning because I haven't got enough tokens in there. So it's going to be l.relationship 2, and then our relationship is going to be the same. Well, let's give it a const. So const lives here. Can't go anywhere else. And I think it's transitions to. That's what we called it. There we go. So we can then say relationship that. And when you are building structs, there's two ways you can do it. There's positional, so you don't actually put the labels in there, and it will accept a positional thing. And there's named, and I almost always use named, because positional is just waiting for someone to come and add something to your struct. And even if they're nice and put it at the end, one of my linters may turn around and say that your struct is not memory optimized and you want to have it in this order, and then you cut and paste that and shove the definition in, and all of a sudden all your code's broken. So I will pretty much always do this. So let's see if that works. Let's see whether... my God, it did work. This is amazing. It's almost like I planned it. So we've got our relationships in there. We've got some stuff. So there's something else we can consider here. If we had two subgraphs, two portions of our graph that sort of look like this, or indeed n portions of our graph that look like this, where we had a relationship of ID and a relationship of named, semantically this is the same. A node with effectively more data in there, and you can do this to the nth degree, but then you've really got a dumb graph because it's a single node with effectively a JSON document in it. But this is known as a property graph. So you're effectively putting common properties onto your node, so you're not having to do graph traversals, which are unnecessary, because it can make querying quite difficult if you're having to query down several leaves. If you can just have one leaf and a few wheres, that becomes better. So let's write some more code. Let's put that in. And this is quite easy, but thus we can turn around and we can say that our node is now actually a. We're going to make it a map string interface. Now, maps in Go behave like most other maps. Probably the only noticeable difference is that they are guaranteed to iterate in a random fashion. And that is done deliberately to stop people relying on the fact that things come out in a specific order with their test data, which is generally a small set, because the random behavior is going to come in when that becomes bigger. Interface, open close curly brace, is the empty interface. Anything will match the empty interface because it doesn't need to have any functions on it, and if you've got extra functions, that doesn't matter, it still matches. So this is effectively an object type in JSON, or a standard dictionary in some other languages. So you've got a key that is a string, and then a type that is anything, pretty much. So we can define our node as that. Something's going to break here. So we're going to have data here instead, and this is going to be a map string interface. And that's now going to be data. And this will work, that won't. Oops. Because map string interface has its own well-defined way of printing out. It's not great, but it'll do for these purposes. And of course, these are going to break, but we can turn around and we can say this is going to be a map string interface, and it's going to be ID of we're going to do a, and name was foo. Oops. And we've got another one which is B. The name is Bar. And we can define that. And I'm just going to stick this in just to show. Just going to stick a link in just to show it. Print the thing out. So we've now got this map in there. So we've got our more complex data, but we haven't actually modeled what I had on screen. What I had on screen was this: two nodes with no relationship. So I'm going to just remove this, and I'm going to run it, and we get no output because our string function is relying on the fact that there are relationships. And now we run into the thorny problem of graph traversal and all of those other things. And all of these are solved problems, and someone else has solved them for me. So I'm going to stop writing my own graph because this is an exercise in almost churlishness for what I'm doing. Now, you may want to implement your own graph in code, because although almost any data can be represented in a graph, not all data should be represented in a graph in code. And I think I'm rare when I'm talking about a database and not going, you should use it for everything. Graph databases are slow to write to disk. very slow to write to disk. And if you've got a heavy write load and a low read load, you may actually be better off using a different database type and just dealing with the slight slowness on the read. Graph databases need to be held in memory, because otherwise you run into huge problems with partitioning. And if you've got a large data set, a large sort of blob data set, that doesn't want to be anywhere near your graph. You might use the graph as an index, and it might have a value of, this is my foreign key in my Oracle database for my blob, because that is absolutely the place where your blob should be. They should not be in your graph database. But it's a wonderful way to have a general purpose way of creating and querying, especially graphs. And it's the querying side that that interests me for this particular session. So we're going to introduce Neo4j. It's this page, I guess, is always using significant power. It is a graph database. It has a query language called Cypher. And it allows me to have a load of balls and lines and arrows and stuff on screen, because we're going to start talking about much more complex structures. And this is actually where this talk dropped out of. So if you cast your mind back to earlier this March, sort of March the 20th, 2020, as opposed to the 768th, I think we are now, we had the track and trace debacle. And I don't know what the problems were. I'm not involved in government contracts. If I was, I would be very rich and not here. But to me, some of the issues seem to be one of incorrect technology. Because actually doing this whole thing of finding people who have been in contact with other people who may be infected is a wonderful graph problem. It's a very simple graph problem. So in a moment of hubris, I decided that I could do this as a talk, combined with compressing a 3-day Go training course and a 1-day Cypher Neo4j training course, all into a 90-minute talk with live coding. So we are going to fail. This is a given. However, I hope to get far enough that you will be able to piece together where I got to in terms of the back end of the track and trace. Front end, no idea. I don't do front end. There are other problems there. This is just the finding the people you need to notify. How you notify that, all of that other problems not going to be solved here. Unless you are a government contractor and can give me millions and millions, in which case, yes, I can absolutely do it. I'll be back in a year. So first of all, I've done a little bit of prep work, because we're dealing with a database and there are some considerations to be had. Not least because with the database there are things that can go wrong, and I don't really care for this talk. If something goes wrong, then I have screwed up, and I wanted to just go bang and say you've screwed up. So while teaching Go, I would say never, ever, 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 ever use the panic keyword. Rule number 1, don't panic. Go doesn't have exceptions, but it does have panic. And you can recover from a panic, but in this case, I don't care. I'm in a state that I shouldn't be in because I've screwed up, so we're going to panic. So I've got a lot of things that just provide very lightweight wrappers around the Neo4j driver and hide the errors from me so you can just have the code. This is one of the downsides of Go. You'll have a lot of this sort of thing, 2 values coming out, then if not equal to nil, do something with that error. And the idea is that you should be dealing with your errors there and then, rather than sort of the Java C# world where you try big block of code, catch exception, whatever. It's like, deal with the error that has happened when it happens. But in our case, we're just going to fall over in a crumpled heap. And it's fairly standard. We've got a set of basic authentication credentials. Do you want me to make it bigger? This? No, this is the shorthand operator. Let me actually just go into my. Is this the right font? Let's go 18. There we go. I've turned ligatures off as well because people seem to hate them. Right, so not equals is, as you would expect. There are different ways of doing variables. So the question for people online is this a not equals operator? No, it's not. You can define a variable by turning around and saying var foo is of type string. You can define a variable and say that var foo, oh, I'm going to have to do var, is a string and is equal to that. You can see already I'm getting this saying the string is redundant, but the compiler can work out that it's a string. I could, now I have to use this definition outside of a function. But inside of a function, I can turn around and I can say that var baz, and use the colon equal, oh, sorry, don't need the var. Baz, and use the colon equal, and just set that to baz. So that it's syntactic sugar, basically. But it only works within functions. Now, I would argue that actually I've still got ligatures on. Sure, I turned them off. Go away. There we go, because that is now a not equals. Right, so, yes, we're dealing with database. I'm just using the default things. I've got Neo4j Community Edition running in a Docker container, and we can connect it. So this just creates a new driver, and if there's a problem connecting to the driver, I've obviously killed the container and not restarted it. We deal with logical connections to it, so I can ask it for a I could go new, it gives me a connection. I can ask for a session on that connection. I can close that connection, although I probably won't. Because I'm using the community edition, I don't have access to multiple databases, so I can't actually drop and recreate fresh databases. But this little bit of cipher just says match all the nodes in the database, get rid of all the links, and then delete all the nodes. It's not quite the same as recreating the database because internal IDs are not reset, and some caches may still, but it's enough for our purposes. And there's a run somewhere as well, yes. There's a run that, again, swallows errors and doesn't require extra things that the other run does. And a result where I can just turn around and collect the results out. Now, Neo uses a binary protocol called Bolt, and you can stream the results back from the database, which is very handy if you've got huge result sets. Collect within the result type just streams everything and gives it back to you in one lump. We're not going to be running into memory problems, I don't think. And again, I'm just swallowing the error. So this is a very lightweight wrapper around the default driver. Apologies if I stumble a little bit over this. I have a massively customized driver that I use day to day that does things that allow me to pass in Go native types and have them populated from my results and everything. So if I'm suddenly like, how do I do this? It's because it's been abstracted for me for 5 years now. I'm back to the bare driver again. So this has been written for me just to not have to worry about the database. So I've got some notes because I'm reasonably organised, and I'm going to go back here. And no, yes, we are going to go back here. And do we care about the no? Neo's got IntelliJ's got a history of things. We can get rid of this code. That's goodbye code. Right. A func main. There we go. So if you hadn't worked out, package main is your main package entry point. It can be, you can only have one package in a directory, and normally the package name is the same as the directory name. It doesn't have to be. There are some reasons why you might want to, but generally don't because awkward. But the one exception is package main. And you can actually have multiple package mains within a Go module if you wanted to have multiple binaries built from your module. And then func main is the actual entry point, and it is nil-adic. It takes nothing, and it returns nothing. So we can pop in our that. You'll notice I've imported the DB package. So a Go module is defined as a module name. When you start writing a Go thing, you'll go mod init. And then typically it uses a Git repository URL. It doesn't have to. It could be something else. But this actually allows the module system to go off and actually go to Bitbucket or GitHub or GitLab and pull things as required. So, for example, here it's requiring this from GitHub, so it will go off and pull version 4.4.1 of the Neo4j driver. That's interesting. Oops, let's do that because the IDE is running in Go 118 now. I created the Go mod file before I looked up things yesterday, and I haven't updated everything. There is also a Go sum, which gets created for you by the package, which is the checksums of all the other things. Unlike some other languages that I could mention, JavaScript, your Go sum is generally quite small, and I tend to write Go binaries that have fewer lines of code than a Node program will have imported packages, something I find brutally funny. Also, while we're just going through my project structure, I have a makefile. Go has built-in build tools, but there's no real make system. And I'm a programmer and therefore lazy. So I have a makefile. I have a slightly more complicated one for my Docker builds, but it's not really much more complicated than this. The really complex one goes out and pulls out what version I'm on CI and populates a few things using LD flags. So I've got version information and builds Docker things, but they're not much more complicated than this. And because Make is fairly ubiquitous and Go is fairly platform independent, I find it's fairly easy to use. The only other thing I've got here is my Linter config. I use a meta linter, so it runs all the linters. And then I've worked out what I don't agree with and turned those off. And I lint my tests, but I've got exceptions for tests. And I've also got exceptions for things like color, because I'm British and I use British English. So I use colour. So we've got our, oops, no, we don't want notes, we want main. We've got our connection to, what's there, blind. Got our connection to the database, and we can start running Cypher. And there's a reason I used the format that I did for the output of our graph, insofar as that Cypher is effectively ASCII art for graphs. And nodes are represented as being inside parentheses, and relationships are represented as being inside square brackets, and your relationships, your links are described using dashes and greater than, less than, so you've got arrows. So you're indicating directionality. And then there are a lot of database type semantics that you will recognize from SQL, and then a bunch of stuff that you'll just be like, don't worry about it. So we're going to look at how we might model track and trace. Now, actually, the biggest problem for this session is getting the data in. I'm not an epidemiologist or anything like that, and I have no idea how to model a pandemic. And I don't have the pandemic data and stuff. Fran's looking at me with that. I'm just a Go developer. So I've got a very naive model that we're going to implement, because actually the querying of it is, I mean, that would be a 5-minute lightning talk, if that. Yeah, thank you for coming to my TED Talk. And we're going to build this model. So the first thing we need is a population of people. While Neo4j is sometimes lumped in with NoSQL databases, I don't like lumping it in with them because it is its own thing. And it has some interesting things in such it's schema light. You don't need to define a schema, but you can turn around and say that nodes with this particular label follow certain rules. And on the Enterprise Edition, you can create invariants and say that you must have these things defined. The Community Edition is less flexible, but we're not going to be using those invariants. I don't even think we're going to use an index for this particular session. So you end up with, if we want to create some people, we want to create, let's define some constants. So we've got const population, we're going to start with 100 people. And so we're going to want to iterate, oops, is less than population I plus plus. One of the other things that people notice with Go is a lack of brackets around for and if statements. You don't have to omit them, but linters will whinge and Go developers will look at you sideways. They're not there, and you get used to it, which causes problems when I go back to other languages. So we're going to want to create our population. And what I'm going to be doing here is using a nice feature of IntelliJ, where I can turn around and I can inject syntax highlighting for a particular language. So what we're going to do is we're going to use the, in fact, like I said, we're going to use the create keyword. So we're going to create a node. We're going to create a node of type person. The reason why it's colon, excuse me, colon person, I could put a variable there. So my person will be assigned to the variable p, but I'm not going to refer to it, so I don't need that. So it's not going to be assigned to anything. This is a label person, and I'm going to give it some properties. And I'm going to give it the property of ID, and that is going to be set to the value of ID that I will pass in later. And that's all I need to do. We're going to just get I've got things happen on save, and so one of the things it'll do is it will capitalize and lint my cipher. So this is how you create a node, or one of the ways you create a node, and then I can turn around and I can say s.run my statement, and I want some parameters. So this is going to be a map string interface, and in here we want an ID that is I. So yes, this particular way that I've got the parameters set up is stringly typed rather than strongly typed, but I don't want to be going through my massive abstraction that I've got and worrying about that. One of the other things to note is you may think that you've got too many curly brackets in that map string interface, but what it is the type is a type of map string and then this anonymous declaration. So we're defining an anonymous type that is of interface open close curly brackets. And then the next set of curly brackets is me saying what's in that particular map. So this has to be a string, and then this can be anything. So if I do this, what it's going to do is going to connect to the database, it's going to clear the database, it's going to give us a session, it's going to run, it's going to, let's be nice, let's close the database afterwards as well. So if I run this, that's going to go away and do stuff. And if I go back here, if I turn around and say match and return n, so that's going to match all nodes. So I've not specified a label, so it's just going to go off and match everything, assign that to the variable n, and return those nodes. And unsurprisingly, we now have 100 nodes in the database, all unlinked, all with an ID. So we've got our population, and we can do things with our population. We can start playing around with how they interact, and I am, because I'm just a little conscious of time, going to go off and grab. Here's one I prepared earlier. Is interact going to work with? So population should be very much the same. Interact, what I'm saying is match a person who has this ID. So your where clauses can go sort of here in this format. There are other where clauses as well. Apologies to the people online, I keep banging the mic. And I'm matching two things here. So I'm matching a person with an ID from, and I'm matching, that shouldn't be R, that should be O. I'm matching a person with another ID. They're two separate matches. And then I'm saying create a link between these two things that I've matched before. So S and O are now the previous matches. I'm going to call my my link contacts, so the label, and idiomatically with Cypher, your nodes are camel case and your links are snake case. Snake case, the underscore, capitals with underscores. Your relationships can also have, your links can also have properties on them. So we can start looking at what's going on. I'm defining a couple of constants, so we're going to say there's 5 days and a 10% probability. I've got some little RNG type functions that I've just thrown together, and we're going to go through our population, and then we're going to say every day there is a probability, 10% chance. So if it isn't, effectively, this is going to turn around and say if it's not our 10% chance, we're going to return. I could have put the probability at 90 there and got rid of the not, but either way. Otherwise, we're going to create our set of properties, so our from and our to. RNG select is literally go off and get me something from integer 0 to size, non-inclusive, not including I. So it won't link to itself. And then we're going to run that statement. So what will happen is, effectively, we're saying every day there is a 10% probability that someone will interact with someone else. And we're going to run this for 5 days. So it's going to clear down the database, populate, it's going to put 100 people in there, and then we're going to link it across. So that's now run. If I run my match n or return n, we've now got things going on. We've got little clusters of people who have interacted, little chains of, and it's, when you think about it, quite obvious why it's mostly chains, because it is a single person interacting with a single other person. So unless you get one person selected quite a lot by that two, so this person is particularly unlucky. They've interacted with one person and have 3 people interact with them, and we can start playing around with the numbers. So we can turn around and we can say, 28 days later, what's going to happen there? Let's run this. It's going to take a little bit longer to run, but not too much, and then we can rerun this query, and ooh, there's a lot of interaction going on there. Now this is a really simplistic model. We've got a small chance that one person will randomly interact with another chance. There's no other things in there, and this is now a big old bundle of knots. So it doesn't take much to start getting your graph really quite intertwined. And this is part of the reason why we've had lockdowns, because we're trying to reduce that connectivity, contacting each other, because this is what happens even with fairly low probabilities. Your graph starts off a few connections on first iteration, and then it just keeps going. Great. So we've got this idea of people who have interacted, but then we might also want to have, for example, the idea of someone who is infected. And we start going off and limiting what we care about in terms of infections. So it's not just has someone come into contact, but has someone come into contact with an infected person. And you could possibly do this in Cypher directly, but the Cypher becomes indecipherable, pun intended, and this is not a masterclass on big brain Cypher. This is actually understanding what's going on. So I'm doing the reads and doing the logic in code, because that's a lot easier for everyone else, and myself included, to understand. So this particular thing is just a little read function I threw together because I wanted to get to grips of how the basic driver does its reads, to be honest. What we're doing here is we're saying match n, so that's anything. I'm returning n.id. So id is one of the properties on n. If id doesn't exist, it comes back as null. And you've got to be quite careful with null in the FJ because null is handled in a well-defined but not quite how you might expect type way. So true is not equal to null, or null is not equal to true. False is also not equal to null. So there are some queries you've got to be careful if you're writing, if you aren't guaranteed to have a Boolean set, going off and finding where true or not equal to true may not work because you've got nulls in play there. So you just need to be a little bit careful of that. And yeah, so we match n, return NIID as ID, so we're just casting that so that it's actually got a nice name, otherwise it would be returned as n.id. And limit 5, I only want 5 of these things back. And what I was doing here was just making sure that I could actually get some IDs. So if we don't clear the database, and we don't populate it, and we don't interact with it, but we do read it, unsurprisingly, we will get a bunch of IDs come back. And there is a reason they've come back in order, and it's to do with the way that Neo's doing its lookups and the way we created those nodes. It's not guaranteed to be that way, but we've got a small data set that we created in order, and it's coming out in order. The reason why we've got a value and true is because the particular get that I've done returns if it found something there, which can be very useful in terms of go defaults has a 0 value for everything, and sometimes you don't know whether your 0 value is actually 0 or not there. So the true false tells you whether it was there. Less of a problem with most of the driver, but a bit of a problem with nil or null. So if the value was set to null, then you know, but if there wasn't a value there, it would come back with false. Right, so we can do reads. So I came up with this idea of doing some interactions. Now, in the best Blue Peter fashion, here's one I was making earlier, and it doesn't work. Oops. Quite. So we're going to fix it. And the way we're going to fix it is I'm going to explain what's going on. This is why I love having junior people around, people who are not as familiar with languages as me, because I look at the code and I go, assumption, 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 why doesn't it work? Whereas when I'm dealing with people who may not have the same context that I do, I have to break it down into simpler steps. And then you go A, B, D, ooh, where's C? There's my problem. So we are going to be building a, oh no, hang on, this is the wrong one. It's model that I want. Let's get review. Oh no, I've done model. Model, okay, so we have our population size. Our population size is 100 people. Our infection chance is 10%. Our duration, again, 28. I may have seen some films on infections, I don't know. And then I've got a couple of maps to find. The reason why I've done this is because I want to have this idea of going to locations, because that's what track and trace is all about. It's about, have you been to a location that someone else who is infected has been to? And with this, we are basically turning around and we're saying that our infected are naughty, and every day they are going to go to the shop. And I've done this because I wanted to make sure that I had some infected and various other things. We'll rein that back later. And then our healthy may visit the shop, school, work, and the cafe. Places is a nice, simple thing where we're just turning around and working out what places we have and creating them, so that I've got my place nodes. And the way we're doing this is we're turning around and we're using a map as a lookup. Go doesn't have, actually it might do now because it's got generics, ooh. But Go 1.7 definitely did not have a built-in way of seeing if a slice contained an item. Because your slice could be of any type, and you can't cast a slice of type A to a slice of type B. You have to actually iterate through it and cast the things internally. So you can go off and write your iterate through the loop, but especially with larger slices, that becomes inefficient. So what we can do is just use a map as a lookup. So what I'm saying here is my locations is a map of type string, and then the empty struct, which is one of the most memory efficient types in Go. And then I'm iterating through the maps that have been passed in. This is my variadic argument. This is syntactic sugar. This allows me to put in 0 or more of that type in my function call, and it will treat this as a slice. So if I don't pass any things in my function call, I will get an empty slice back. Otherwise, I will get the slice of. It has to be the last argument. And it is quite useful because it saves me having to wrap things up as a map. As a slice, pass them in, and it makes it for easier doing of things. And you'll notice things like format use it quite a lot because you've got your format pattern, and then you have n, where n is undefined, things that go into that pattern. So that is a string, and then ... interface. So we're going to take a set of maps, and what I'm doing there is I'm passing in my healthy map and my infected map, and the reason I've set it like this is because I might actually want a previously infected set, or another set of people, so I can just pass them in. It ranges through the set of maps that's been put in. It then ranges through the things in the map, so iterating through maps is the same. You use for. It's also variadic in what returns. It'll either return the key if it's a single, or if you do k, v, for example, it will return the key and the value. So we're going to I only care about the key, and if I have something in my locations map, again, another variadic type thing. If you just have one variable on the left-hand side, it'll give you what's at that location. If you have two variables, it'll give you what's at that location and whether that was actually there. So if it's at the 0 value, was it set as the 0 value or not in the map at all? And idiomatically, we call that OK. So we're saying, is it in that map? If it is, we continue. Now, I hate with passion the continue keyword, but for the purposes of this, it's fine. If it's not in the map, we go off and we create our location node. And then we add something to our locations map. And again, it's just the empty struct. We care about the key, we care about the lookup. And this is marginally slower if you have teeny tiny slices and faster for sizes of n greater than not much in terms of lookup on things. So we can now dynamically define our places in our database. So we have 4 places. Patient 0 is a random person in the population. We will turn around and say, you are now infected. Okay, this is doing the call of places. So this is my session, and then this is my variadic list. So this could be that, which is not going to do anything because it's going to be the empty size. With that, it can be 1, it could be n. Now we're going to iterate through our population, and we are going to create our people. Same as we did before, except this time I'm passing in another parameter, infected, which is Boolean, and infected is set with our set of parameters that we pass in to be whether or not that person is patient 0. So you start off with 4 places, 100 people, one of whom has the lurgy. And then we are going to iterate through from day 1 to our duration, and we're going to iterate. We're going to increment the counter. And I've got some queries here where I'm just going off and finding my set of infected people and my set of healthy people. And those sets are, unsurprisingly, the people who have infected set to true and the people who have infected set to false. No parameters passed in there, so nil going in. And I'm ranging through those, and I'm through my infected people. I'm getting the ID, so this is my result set. So I'm already collecting all my results out and getting them, so I'm pulling out the ID from my set of results. So this is my set of infected people. And I'm saying visit. So visit takes my person and decides on that day, are they going to go visit a location? So we're iterating through our infected people, and we're saying, on this day, this ID, this person, work out what they're infecting. So this is my map of where they could visit. Bunch of things there. Again, if I were writing this properly, this wouldn't look like this in terms of arguments, but for the sake of ease. So we're going to iterate through our places map. We're going to go through the places and the chance, which is the key and the value. If our chance occurs, if our percentage occurs, if our probability occurs, then we've got this statement where we are matching the person and the location. Now that is a query. And normally you would have return at the end of that, but I want to do more things with those. So I'm saying, rather than return, with these two items, go off and merge the pair of them. So find this node and find this node, and see if there exists this link, and if there doesn't, create it. And the reason why I haven't just done merge p person ID is because if it doesn't find that pattern, it creates the whole pattern. And that ends up with me having lots of locations around, because it's found the person, but it goes off and goes, well, I found this side. I had a bug earlier where, so I'm matching, grabbing my two nodes, and then merging the stuff in. And yes, person, location, place, and day, going in there, and you can see that I am using format.println as my debugger, because that's the best debugger in the world. Go does actually have a very good debugger, but I tend not to like delving into it, because at that point, something's gone wrong. It's a hard problem as opposed to a simple problem. So that will wire up every day this set of person has visited a place. So that should be our... I'm just going to comment this out. And where was my... There we are. Yeah, that should be my set of visitations of people. So we should, in theory, see our population, see our places, and see links between those. So let's see what actually happens. Drum roll, please. So that's going off and doing its thing. There's quite a lot of queries going on in the background, and if you remember rightly, when I said that the graph databases are a little bit slow to write. The enterprise version is faster, and if it's not running in a Docker container on a Mac with very limited resources, it is also faster. We run this at scales of millions of nodes. It's been tested with billions. The limit generally becomes how big's your wallet. So let's pull the query up, and already I can tell there's a problem. This is one of the great things about graph databases, is you can tell there's a problem just by looking at it. We're expecting there to be some visitation of places by people. Now at the moment it's a bit hard to see what's going on. There's a lot of dots on the screen and they're all grey. So there's this wonderful thing that we can turn around and we can select this, and we can select this, and we can turn around and say the people are going to be this reddish colour, and places are going to be this bluish colour, which hopefully is, so we've got our 4 places and we've got our nodes, so we know our creation is working, our visit code is not working for whatever reason. So let's try and work out why. So we've got a statement here. I'm just going to go copy into. This, and we can put in some test data. Oh, you're not. Oh yes, because I've got other things there. So I'm going to say that I want to match a person with ID 1, and the location name is going to be shop, because I know there is a shop. And what I tend to do with Cypher queries is, because it's a graph, when you do that match, you're getting n results back. then when you're doing that next step, it's going to do it for each of those end results. And you can actually end up with quite large data sets very quickly because you're traversing the graph and doing actions at each stage. And if your problem's at the top, you might not be able to see the wood for the trees. Again, pardon the pun. Because you've got so much, I'm disapproving looks, I love it, so much data. So I'm going to just do a return P and L. No, I'm not going to return P and L. And you're not liking that. Why are you not liking that? Ah, right, okay. It's not liking it because it's saying that it can build it's building a Cartesian product of nodes, but actually it's not because I am anchoring my query. It could possibly be building that Cartesian product because it's doing two queries. And I mean, we could make it. We could make it shut up. There we go. With P, L. There we go. Let's get rid of all the warnings. Warnings are always a bad sign. So, no warnings on there. I am expecting now that to return. Right, that has returned the two nodes I expected, so I'm not going crazy. Excellent. The next part of the puzzle is this merge, where we're saying merge those two. And we're just going to say day one. And that's fine. Let's run that. That created a relationship. So if I turn around and now say, match that person, return P, that has matched my node. And one of the nice things you can do with this browser is you can click on a node and expand the relationships coming out of it. So I can now see that those two are connected. And there was a minor change to my cipher, but I don't think that was the issue. I think the problem exists in my code. Shock and horror. Let's just... Oops, going with P. No, with P. Then match that with PL. I am just going to rerun this in case it has been something stupid, but I don't hold out much hope. I think we're going to go back into a stage where we've got no nodes. Well, sorry, no links. So off you go and delete everything like that. And we will now rerun our was it command? Control, oops. Command. What's it? Yes, match and return it. And we have 0 relationships. So it is my code. My code is at fault, as is so often the case. Right, so the first thing, am I actually calling my query? Let's have a look. Let's go and just format up them params. See what's going on here. Rerun that. Absolutely, yes, I am. Quite a lot. Is my I think I may have bing. Is it because it's treating ID as a string rather than an integer? Let's do so ID 1, return n, ID 1. I wonder, because person is coming through as a string. What if I just turn around and say that's an int? Let's do that. You're now an int. You're going to complain up here because I'm doing that. You're going to be an interface. Right, so what I can do here is I can turn around and say that this is an int. And that will panic at runtime if it isn't. But we're reasonably sure that it is. So that should be okay. There is a way of doing this where you can turn around and do again, the sort of the variable comma OK, and that won't panic. That will send you a false if it hasn't cast. But this is slightly different to turning around and saying int with the variable, because that's basically saying create me a new int with this value, and that is restricting what it can be. This is take what I've got and turn it into an int with a sledgehammer if need be. Right, let's try that again. Let's get rid of my format.println. And this is one of the problems I have with bouncing between Go, which is a very strongly typed language. Neo4j is very not typed at all. Oh, it's an int64, not an int. So with Go, int is a alias. It's an alias for int64 on 64-bit machines, and it's an alias for int32 on 32-bit machines, which may be something you need to consider. I always run on 64-bit machines, and I know where all my code's been deployed, so I treat int and int64 interchangeably. However, right, you are not allowing that, so we'll just turn around and say you're an int64, and then we're going to then turn around and turn that into, this is getting nasty. This is why I have my heavily customized driver. Let's have a look. Let's try running that again. That's looking better. That's looking more hopeful. Yes, it's finished. A little bit. So if we return, oh no, we don't want that. Let's just want to match in return in. Yes. No. Yes. Oh wow. Wow. Right, okay. There are some links there. There is some interaction. And people have visited places. Right, so now we actually care about who's infected, because this is a big old ball of nothingness, and really it's going to... It's not going to tell us much. So let's turn around. Let's find our P person. Which is person, yes. Oops, present person. And infected. True. Return in. Nope, return P. I haven't put in the infection bit, that's why. It's working. Right, the last piece of the puzzle, the bit I commented out because we were debugging the. We need to infect people. We need to turn around and say that you can get infected. So we have this idea of visited. Visited is doing a slightly more complex lookup, and this is where the whole graphy nature of what's going on comes into play. So we're saying, find me a person that is infected, who has visited a location on the day that we've passed in. And actually, I'm going to do this the other way around. Day -1 has been there yesterday. And someone who has visited that location today. So this is finding me a sort of a V shape where you've got two people and a location. Both people are tied to the location node, and we're narrowing it down by the person on one side needs to be infected, and the person on the other side needs to have come the day afterwards. So the model we're saying here is if you go to somewhere where someone has been infected, the next day you are getting infected. Very naive, but it's a way of spreading the infection and having that kind of after, the cause and the effect. And these kind of queries start getting harder in relational databases because everywhere you have a relationship is effectively a join. And when you start getting out to more than this, the number of joins you have in a relational database is slow, whereas in a graph, this is just pointer chasing. You are just looking through a set of pointers and going, that one, off you go. So we are pulling out the set of people who have visited, and then we're iterating through that set, and we are saying, find the code, there we are. We are saying, if you've not had your infection chance, then just continue. Otherwise, we're going to get the ID for the person who's infected, and we're going to set their infection flag to true. So, 9 minutes left. I'm actually going to get to the end, I think, if it works. Work. That's run. No, that has not worked. Right. Let's work out what's gone wrong. Visit head is probably the first one that we want to. So let's just. Let's do this. So this is going to be the first thing that we're going to work out is whether or not that's actually pulling anything out. And no, it's not. So there's something wrong with my visited function. Let's stop that for now. We are running this query. Let's pull that query into here. Actually, before we do that, let's just properly reset the database. Let's get rid of that print. Let's reload everything. There's one problem of killing the process halfway through as my database is now in a funky state. So let's get that data back in there, and then we can run this query, and we're going to say that our day is going to be day 1 there, and our day is going to be day 2 there, and we're still getting a warning on there. Provided key is not in the database. Is it that key? On. Not. Oh no, it is on. Where's my creation? Right, that's day, and I've used on. Right, that'll be why. Oops. Day. Queries incorrect. Visited day. That's interesting. Going back to the Babel, and I'm going to let it sort itself out. The problem with having so many links is it's now trying to display all of these links in some kind of meaningful fashion. Right, it is on, not day. So that's the problem. This is on, and this is on. Let's just go up and oops, put that in. So let's change that to on. Let's change that to on. Still complaining. Why are you complaining? No. Day 1, day 2, run that. Yes, that's returning things. So if we back up here, comment doink, and press play, with 5 minutes left, it's run. No. You're going out. Are we correctly? ID. Oh, again, this problem. ID's coming out as. Well, it's coming out as an interface. Let's cast that to an int. No, can't. Dot int 64. Let's just try bludgeoning that in. Let's rerun. No! Fell at the last hurdle. However, hopefully you can see where I'm going with this. It's brutally easy to turn around and say, right, find me the set of people who have been to a location where another set of people who have been tagged as ill have been. It's a simple query. And in fact, we're running that query in order to try and find the infected people and run them. And that particular query was working. As I said, the hard bit is not the trace part of the track and trace. That's a one-liner. The hard part is modeling all of this stuff in the first place and getting it into the database. But hopefully that has been a sort of a crash course in Go, a crash course in graph databases, a crash course in Cypher, and a crash course in why you should not update your everything, because I also updated Docker yesterday as well, and my version of Neo4j. Because why not? Why not? I was in by that point. It was like let's just. So everything's on the left in Neo now. But yeah, hopefully that gives you an idea of what you can do and the power that you can get out of this. And there's a reason why Facebook has their social graph. Because this is what they're doing. They're taking that graph of you and your connections and their connections, and it's very, very easy to actually get a whole load of information from very little data by sticking to a graph and playing with it and running these queries. But I have run out of time. I want to leave a little bit for questions and or stunned silence. So thank you very much for putting up with my wittering for 90 minutes. Thank you. Does anyone have any questions? No, you will not get the last 90 minutes of your life back. No open questions online, lots of stunned faces. I always have stunned faces at the end of my talk. I don't know how to take that. Hopefully lots of people thinking about things. And I am now going to go and relax. Oh. Oh, apparently Roger on the Discord has said, did I spot an on in the... In the ooh. Make it a word. I'll do all of that. That's all. There we go. I'm buying him a beer if this works. Any questions? Roger will be answering them. Is he at the conference? Right. He's online. Next year, Roger, I am buying you a beer. Thank you very much. At least he was paying attention. Yes, it worked. Hurrah. And the scary thing is that 83 of our 100 people are now infected. So that's 28 days. It's and you can extend this further. You can start having people recover and be less susceptible and so on and so forth. But you can just absolutely run with this.